This is the fifth and final video of the further integration topic, and in this lesson we're going to be looking at integrals involving inverse trig functions. But before we get to the integrals, let's first review what the derivatives of our inverse trig functions actually are and how we get them. Starting with y equals inverse sine of x. Since we don't know how to derive this directly, let's switch things around to something we're more familiar with. And let's write x is equal to sine of y. Then we can find the derivative with respect to x over y. So dx to y is going to be cos of y. But remember, ultimately we are after dy dx. So let's reciprocate both sides. So we get dy dx on the left, and we get 1 over cos y on the right. We want our derivative to be in terms of x, not y. And we have the link between x and y here. So how can we change our expression involving cos y to involve sine y instead? Once again, we're going to use the Pythagorean trig identity. Cos squared plus sine squared is equal to 1. Making cos squared the subject gives us 1 minus sine squared. And if we just want cos of y, we need to take the square root of both sides. This means we can now replace cos of y in our original working out with the square root of 1 minus sine squared y. But since sine y is just x, this means we get 1 over the square root of 1 minus x squared. And so this is the derivative of inverse sine of x. Now that's great, but what if we have a slightly more generalized version? Y equals inverse sine of x on a, where a is some constant value. What does our derivative then become? Well, to find out, let's go back and adjust our proof. So instead of starting with inverse sine of x, let's start with inverse sine of x on a. So this means our second line becomes x on a equals sine y, or x equals a sine y if we multiply the a to the right hand side. Deriving, we will then get dx to y equals a cos y, and so when we reciprocate both sides, we get dy dx equals 1 over a cos y. Stopping here and coming across to this working out, we can once again start with the Pythagorean trig identity, just like before, and rearrange it so that we get cos y as the subject. But now we want to substitute out a cos y. So let's multiply both sides of this by a. And if we then absorb the a into this radical function underneath the square root, well, it needs to become an a squared then. And if we expand so that we have a squared times 1 is a squared, and then a squared times sine squared y, well, that is simply a sine y all squared. So that means back over here we can now adjust this to look like this. But since a sine y is just equal to x, we can write our final derivative as 1 over the square root of a squared minus x squared. And so we have our derivative for inverse sine of x on a. So what about inverse cos and inverse tan? Well, these can be found through very similar proofs to what we just used. I would encourage you to have a go at seeing if you can come up with the derivatives for cos, and inverse tan yourself. The only difference really with the proof for finding the derivative of inverse tan is that when we get to using the Pythagorean trig identity, we need to divide through by cos squared each and every term, so that we get a relationship between tan squared and sec squared. So this first term becomes 1 plus tan squared theta equal to 1 over cos squared theta, which is sec squared theta. And so we use this relationship in our proof for the derivative of inverse tan. Now the final part of our little review here, what if we don't have x, but rather we have some other function of x? In this case, we would need to apply a chain rule. And so rather than going through the whole proof again, we can just alter these derivatives here. So instead of x, we have f of x. And then we also need to remember to multiply by the derivative of this particular inner function, so f dash x. And there we have it. Okay, so let's take this now and flip it all around and look at the integrals that will give us inverse trig functions. So that is, if we integrate expressions that are of these forms, we'll go back to an answer like these. Now, one thing I want you to keep in mind is the similarity between these two expressions. The only difference between them is this minus here. And for that reason, when we look at what is provided on our reference sheet, we see that only these two are provided. If we were to put in the inverse cos integral, that would be fine, but we can see that simply taking this negative out the front gives us the same expression as above, and so we can just apply this result. Alright, it's example time. We're going to do 2, and let's jump into the first one now. Find the volume to 2 decimal places of the solid of revolution formed if this curve, y equals 1 over root 1 plus x squared, is rotated about the x-axis from x equals 0 to x equals 3. Now, remember when we are rotating about the x-axis, this means we want to use this formula. Volume is equal to pi, and then we have our integral y squared dx. So let's come up with an expression for y squared. We have y, so if we square both sides, we can see that 1 squared on the top remains as 1, and then underneath the square root, when we square that, it disappears. So this is the function that we want to integrate between our limits. For us it'll be 0 and 3. So the volume is equal to pi outside the definite integral between 0 and 3 of 1 over 1 plus x squared. Which of the inverse trig functions will we get? Well, whether from memory or by using a reference sheet, we should identify that the result of this integral is inverse tan. It's the one that doesn't have a square root function on the bottom. And so we can now evaluate using the fundamental theorem of calculus by substituting in x equals 3 and x equals 0. Now tan of 0 is just 0, so inverse tan of 0 is 0. So we can ignore that one if we want. But when we multiply pi by inverse tan of 3, we get 3.92. Remember, we're going to 2 decimal places. And this is a volume, so we want to finish it off with cubic units. Okay, example number 2. Find the integral of 1 over the square root of 9 minus 4x squared. So this one looks a little trickier down here because it's not nice and neat. So what would we like it to appear like? Ideally, if we can get this denominator to be in this form, then we can more easily apply our rule. So what do we need? Well, we need this x squared by itself, and at the moment it's got the 4 attached to it. So let's factorize out 4. When we do that, keep in mind that we have to adjust the 9. So if we divide 9 by 4, we are left with 9 over 4. So notice that if you multiply these back together, you would simply get 9, which is what we want. But the real reason for factoring out that 4 is we now have a minus x squared. The next thing to do is to drag the 4 out from the square root. So what is the square root of 4? Well, that's 2. But then we also want this value to be a squared value, right? We're after a squared minus x squared. So what is it that we would square to give us 9 over 4? Well, the square root of 9 is 3, and the square root of 4 is 2. And so now this looks a lot better. It's a lot easier to use our rule. So finally, we'll just drag that 1/2 out the front of the integral. And we're left with 1 over the square root of 3 on 2 squared minus x squared dx. And so now we can integrate. We notice that this matches up with inverse sine. And in this case, it will be inverse sine of x on a. But our a value is 3 on 2. And so if we want to remove the fraction within a fraction, we can say that this is 1/2 times inverse sine, and instead we'll write this as 2x on 3. And that's our final result. And thus we are finished the further integration topic for extension 1. Great work.